to formally introduce ourselves, we're the Inferno System Group, and we're an online fire notification system. So to meet the team, I'm Pamdeep Singh. I am the project leader, manager, firmware developer, and hardware advisor.
I'm Florian. I'm the software developer and requirements specialist.
Adam Pastor, software developer.
Benjamin Blankstein, hardware designer.
And this is Lovi, fellow hardware designer.
Nick Vincenzo, fire alarm advisor and hardware technician.
So to talk about what topics we're going to go over today, we're going to recap our system overall to remind you guys what we intend to do. We're going to go over the configuration of the fire alarm panel. We're going to break down our progress in terms of hardware, firmware, and software. We'll go over cost analysis, and we'll talk about problems we faced and how we tackled them. Then we'll go over the demo. So overall, our project is an online notification system for fire alarms. We wanted to provide peace of mind to businesses as well as tenants in larger apartments and residential areas. We wanted our system to be automated. We wanted it to handle data flow and communication automatically without any user input. We wanted it to be versatile in the sense where it's plug and play. We wanted our system to go into a pre-existing infrastructure and just work. We wanted seamless communication, and we wanted an N-infinity system. Basically, we wanted to counteract any errors that might occur and basically deal with it. So for fire alarm systems and control panels, Nick will carry on from here.
Our fire alarm control panel is configured using initiating and indicating circuits. These are detection circuits and signal circuits. Initiating circuits include manual pull stations, smoke detectors, ion and photo smoke detectors, as well as heat detectors and rate of rise heat detectors. For our particular application and our setup, we used only a manual pull station and an audible visual alarm, as well as our integrated detection circuit. Our panel uses normal residential, commercial power, which is 120 volt AC, uses normal outlet. The panel is configured to enable the setup of multiple initiating and indicating circuits. So one panel, you can configure a whole building, a business, something like that. Our particular case, like I said, is one pull station and one audible and visual. Okay, two types of fire systems are the SLC and conventional. We use the conventional. You can see in the diagrams in the conventional system, it's once you're notified of a problem, it's going to just give you a particular zone, not a specific indicator, whereas an addressable alarm system is going to give you a specific detector.
Alright, to start going over our hardware progress, this is the basic setup of our Inferno system. So as the left-hand side is our fire panel supplied by Miracom. The top right of our fire panel is what we call the initiation zone. That's connected to the positive and negative terminals of our pull station. The bottom right are our indicating zone, which is connected to the positive and negative terminals of our strobe light. So that you'll see this more in the demo when you pull down the pull stations. The fire panel goes from 1 volt output standby phase to a 28 volt rise. So the most important part of this setup is our detection circuit, which then takes this 28 volts rise and makes it easier for our Arduino boards to be able to read it and be able to display the signal to our GSM and our gateway board. Then we'll be going over the technicalities.
So here's the schematic of our detector circuit. We have 2 positive and 2 negative inputs, 22 ohm resistors coming through as well as varistors, a transient voltage suppressor diode, a Schottky diode, 2 BJTs, a 33 ohm resistor, 2K resistor, 10K resistor, a 6-pin optocoupler, a 0.1 microfarad capacitor, and LED, as well as another 274 ohm resistor. And so on the output is pin 4 of the optocoupler, is where we read to the detection board. So this is the breadboard setup of the schematic I just pointed out. We have a rail here that's 3.3 volts coming in that we used in Arduino Uno board for the 3.3 volts, and without anything coming in from the input, we get 2.7 volts. And when we put 28 volts in, which is what comes from the fire alarm control panel, when you actually pull the pull station, we get 200 microvolts from our output, which then signals the detector board to say there's a fire.
Just to quickly go over the backup power supply. Luckily, our fire alarm panel has its own built-in 24-volt supply, which provides a continuous supply voltage to our detector board. But in terms of the gateway board, we have to consider that it's connected to a PC, so it needs an uninterrupted power supply to be able to keep on.
So in terms of the firmware, what we want is the detector to basically sense the output coming from the detection circuit and basically execute certain instructions based on the voltage value. If it detects the millivolt values, it will send the instructions for fire, where it will send a mass text message to certain individuals. It will also then text GPS locations in a certain format, which we'll discuss later on, to the gateway board. And on standby, it will keep polling and read the voltage values until it detects a certain voltage change, which is the 2 millivolts to the 2 volts to 200 millivolts, where it will then set to fire. For the gateway board, it will split the SMS message, the string that comes in, so it could define latitude and longitude values, where we'll then would upload to a server for GeoJSON instructions. So for the firmware boards, unfortunately, something we'll talk about later on is the fact that we're using Arduino along with FONA. The FONA breakout board will be using 2G GSM, and it will have GPRS location services. You will be using UART to communicate through the FONA, and combined with the Arduino Uno, it will behave as a detector board. The Feather 32U4 FONA will be a microcontroller that will act as a gateway board, which will receive the text messages from the breakout board. Now the Feather, with the correct drivers and drivers files and libraries, will be able to use the Arduino IDE, and because of the small form factor, it's just plus side to it. For the detector board, we'll be using AT commands. We define the FONA as a GSM modem. From there, we then define the format for the GSM to be text messages, and then we will lay out the phone numbers. From there, we would have to run a loop so that it could go through those definitions again, and then send out the specific text messages for the alerts. Logic high, fire, logic low, standby. And because, like I said before, because of the nature of the AT commands, we had to run a very awkward loop. So for the gateway board, we'll be using the same AT commands to find it as a GSM modem, but after receiving the text, we will define the input coming in as a variable, and then we'll split the variable depending on / character. After the characters before the / will then be defined as a longitude, and any characters after will be defined as a latitude. And the gateway board will act as a hub for detector boards in multiple areas.
So I'm going to discuss the software progression, starting with the Google Maps API. The API, we needed to place the marker in the location of the fire, as well as an info window saying specifically where the building the fire is for the zone, as well as a button to link you to the hazard history of the building if there were fires before, and how they were handled, if there's any still existing damages from them, and further on. The geolocation in the zone, as I said, and reverse geocoding is what Patandeep was talking about, where you take the longitude and latitude, and then you then convert it to a street address that is pre-registered in Google Maps. We integrated the Google Maps API onto our Wix website, which gave us a free host for the Inferno system, where you will see where it stores the hazards and the histories, as well as displays it and acts as a database server. These are screenshots taken directly from the Wix website, where we also are marketing the product itself and comparing ourselves to competitors and showing how we are different, how we are better, as well as showing what goals we wish to achieve with a product. And then the screenshot on the right is the hazard overview. That's the API after the fire alarm is pulled. If you click on the marker, you will then get the info window, and it then will link you to the history, as I said earlier. We use the SIM808 board to communicate, which was in the detector board, which then communicated with the gateway board, which acts as a hub to send everything.
So something very useful about the Google Maps API that we use is that it's open source, it's accessible to anyone. But in addition to what we were given, we were able to do simple functions that you could find on your Google Maps application, for example, like when you drag the map to center your view on a different area. That had to be, we had to do that on our own. Also, that little pin right there, or a custom emblem, takes way more code than you would expect, but we got that done as well.
So it's just some stuff that reiterated that Adam said before.
Yeah. So what we have right now for our GPS is a static location. So the consumer, for example, would put in their location, and that's how we would be uploading where a fire would appear onto Google Maps for now. However, future applications of this project could be enhanced using the GeoJSON file. It's a geographic JavaScript object notation file. Basically, what it does, it takes the typical coordinate system that you might see on maps that we're more familiar with, and what we're familiar with is the degrees, minutes, seconds coordinate system. However, that is hard to read for a computer, so it converts it into decimal degrees, which is just this what you see here, which is much easier. So a function in the GeoJSON file is linear ring, and the way that this can be used is we have this donut here as an example, right? We know that a donut has an exterior ring and an interior ring, and you'll see how that's used in the next one. So last year, if you remember, we had a fire not too far from the Leo building. There was a fire. A house, I don't know, blew up something. It was really big, and the radius was in this immediate area. So the thickness of this border of the circle is where officials would cut off the area to pedestrians. Now, the second circle is an area that what our application will do is we'll send this information to Google Maps, and anybody who's using Google Maps routing will see this. And the second circle is basically saying, avoid this area, because although it won't be as dangerous as in here, there will be heavy traffic, and there also will be hazards.
Just to piggyback off of what Adam was saying, if you were to view the interior and exterior rings as hot and cold zones, this particular event was a fatal fire for a member of service. So that interior ring would be closed to all pedestrians, and it would be cordoned off by both police and fire personnel. For our end users, you have the secondary ring, which, like Adam was saying, it could indicate either areas that are potentially close to pedestrians, have additional hazards like down power lines, any kind of like a manhole or a transformer fire, and otherwise a congested area.
So some of the financial aspects, I'm going to go over the prices of the components we used. It says 6 transistors, but we only used 2 on our detector circuit. We just bought spare in case of burning some or blowing them, but we didn't. The diodes as well, they're very sensitive. While measuring them, if you touch them with another component, they usually spark up. So we bought a lot of extras for those. The T-Mobile SIM card were $10 each, but they were prepaid. Since we're only sending text messages, we put $10 into each, which gave us a good amount of 30 text messages on each phone line. And the GSM components were the most expensive since they had the modules directly implanted on them. They were the most expensive in the $50 ones. The Arduino Uno was supplied by the school, but the cost online is about $20.
Also, in terms of financial aspects, because our system's 2G, and 2G is kind of phasing out, in terms of upgrading to a 3G version of it, it would add approximately between $100 to $150, being that each 3G phone now would be approximately $20 to about $60 more. In terms of 4G, that's where it gets really expensive. It could an upgrade could cost between about $200 to $400. But in terms of the monthly costs, 3G and 4G would be more reliable and would actually be a lot more cheaper. In the situation where monthly costs, we saw plans where 4G capable networks were giving us $3 a month, $3 to $10 a month plans, while prepaid it was kind of getting expensive. So some problems and solutions.
One of the problems we faced when configuring our fire alarm control panel, when we wired the pull station, we used 12-gauge stranded wire, and we had a different thinner gauge going to our audible visual alarm. So while our circuit was active going from the pull station to the board, we could not get an audible or visual alarm. This was corrected once we matched the gauges of wire, and we did get an output signal.
So some of the problems we also faced was, of course, like I said before, the lack of 2G GSM. Since T-Mobile is the only one that offers it in America, as well as Ting, it was still a little pricey, more pricier than we expected. Another issue was AT command syntax. Something very small, but something that cost us about a few hours was the fact that I didn't include the country code, the +1, into the code. And it was just not working, and it was something very stupid, but...
We assumed that since we had the T-Mobile SIM card in USA that it would just carry on with it, but we later figured out that that was the only thing with the code. And then to add on, the reverse geocoding is a lot harder than you think. It's we actually didn't get to fully implement it, as we couldn't get it to fully convert them from moments, seconds to decimals. But that is something that we definitely have looked into and would have added to product for time.
So here we were able to use an online web application called Smart Sheets to make a feature prioritization and roadmap Gantt chart. So here we have divided into hardware, software, firmware, the tasks, followed by priorities, start dates, end dates, status, and who the task is assigned to.
We just wanted to give a special thanks to Mircom for sponsoring us and supplying us with the fire alarm control panel, as well as the strobes and the pull stations, the backup batteries, and a couple other components. We also want to thank Manhattan College for giving us the opportunity to work collectively on this project and to get our hands dirty with the fire panel. And a special thanks to Dr. Hussein, who just stepped out for for supporting us and helping us through this project. And the system demo.
It works.
Okay, let's play on the phone. In the present.
Here?
Yeah. Sorry, guys. Go hover over it again. Okay, then so that was Nick pulling the handle. The voltage rises. The detector circuit then turns on the strobes. And then it starts initiating the code and sending out the text messages to the registered numbers. Being that it is just a 2G network, every time we tested it, not every phone got it, it would alternate. For some reason, Pav's phone always got the text message.
Because that was because it was the first one in line for as priority.
But it would sometimes go first two and leave the last ones, and then sometimes it would do the first one and the last one. And then if it detects the fire, the marker is then added onto the Google Maps API, which will be shown in the view. And then once you hear Nick turn off the fire alarm, you see the marker disappear as well.
And that was an intended function. Unfortunately, since we didn't have time to create a database server, we couldn't create the hazard history function that we wanted, as well as implement more markers or more features on the Google Maps API. presentation. Anybody? Yes.
I have a question. You are talking about detection fire system. What kind of sensors are you using to detect the fire?
Well, it's not necessarily detecting the fire, but the fire panel is the way the fire panel is wired. It has its own sensors. It has its own heat detectors. It has its own pull station.
What kind of sensors yes? I mean, this is my description of the sensors. And I'm asking you because there is a false alarm
Yeah.
issue. When there is fire, one of the critical problems is the false alarm. And this could be part of the design or not?
So we actually thought about that. I couldn't develop it in the firmware because of personal issues, but basically what it would do is it would keep checking the voltage, and until it confirms that the voltage level is in a certain range.
I'm referring to something deeper than that. When you have fire and there is the environment, lights, etc., sometimes this confuse the sensor and start emitting false alarm. You have to be sure that you're detecting fire and not, illumination variable, etc.
Yeah, so maybe they didn't clarify this from the system. The part responsible for initiating this alarm is the fire panel. It's not their part. And the fire panel is responsible to detect if this alarm is coming from sensor or something like hazards or something. And after that, the fire panel will give them their system the
So
order
this
to do
project is the fire alarm and after.
It's
This is what my
beyond the
understanding. This was my understanding.
Yeah.
So don't,
Yes.
so clarify this because some
Clarify
things
this.
will be the detector circuit and this is not the case, So I understand what you do. I suspect it actually, It is very good project, but clarify to the audience. Thank you.
Any questions?
That's one quick question. You guys mentioned something about the financial aspects. Have you considered other commercial
Very good
products,
job, man.
like
It's very good.
any other similar products in the market, how much it costs compared to the financial?
Well, rather there's actually not anything similar in our.
Nothing.
Yeah.
It's
and-
new in the market.
Yeah, the closest thing would be the app Citizen, which requires a user input to report crime or hazards in the area. However, the fact that it's only in specific cities and some certain cities also ban the app because of vigilantism or some cases like that. But in terms of our system, it's actually a novel system. It hasn't been, it's original. It's one of a kind.
Yeah.
So, no problem.
Okay, thank you guys. Okay, so we have the third group of